Hello, everyone. Let us start our afternoon session. And it's a pleasure to introduce Mikhail Kapranov, a well-known expert in representation theory, algebraic geometry, category theory. And he will talk about algebra of the infrared secondary polytopes and perverse schobers. Let us welcome.
Thank you very much, and I should start my talk by thanking the organizers of this Congress for putting it together, for recognizing our work, and for providing the opportunity to present it to this audience. I am a mathematician, so whatever I say about physical aspects clearly is based not on less than full understanding, so I ask for forgiveness in advance. And I'll start with discussing the framework of supersymmetric theories, which are here, of course, as I said, it is less than full understanding, but at least I need to sort of speak in a coherent way, so this would be the introductory slide. So we consider quantum field theories in 2 dimensions, and we consider supersymmetric theories, which means that 2 space-time coordinates are complemented by fermionic coordinates, and we say when we say 2, 2, so in general this number n also it's 1 integer or 2 integer that refers to the number of spinors 1 or 2 in the corresponding dimension. So the principle of supersymmetry is that we take square roots, we provide square roots of the space-time translations. And the simplest square root is what I say right here in this super world. There is a square root of operator d over dx. It's the simplest one-dimensional supersymmetry, something like this. So its anti-commutator with itself is the derivative. In two dimensions, we have slightly more such roots. So and the anti-commutators correspond to the give. Well, in this notation is Hamiltonian plus momentum, Hamiltonian minus momentum. What's important that anti-commutator of, because it's 2 new generators, they normally would anti-commute with each other, but in reality they don't. There is some kind of central charge anomaly, and this is the central charge of the theory. So what somehow general formalism, as much as somebody like me can understand, is that we're looking at the infrared limit. So the infrared means that the wavelength is very high. So we think of large, kind of large distances. And in the infrared limit, naively, we have vacua of the theory and some tunneling phenomena between those vacua. But what is vacuum, again, requires some being made precise. Of course, for experts, it's clear, but very naively, vacuum, you say it's a vector with minimal energy. How can there be a nonlinear manifold of vacua? But really, what it means that a vacuum, first we are talking about theory on unbounded Euclidean space, and in order to make it completely defined, we need to specify something at the boundary, and then it's a fully defined theory, and then it has a vacuum. So really, the modular space of vacuum is really the modular space of fully defined theories, and as such, it can be a nonlinear manifold. And in other dimensions, it becomes a very interesting manifold, which has been studied, but in this situation, we are interested in the case when the set of vacua is discrete. And especially it's true when theory is massive. So again, naively, massive means that some quadratic form is non-degenerate, because this is the meaning of the mass, some curvature of the space. And if something is non-degenerate, that the critical points are isolated. So, and then we have a discrete set of such critical points. And we can assume, for simplicity, there's a finite set of such critical points. And in fact, it may be interesting to generalize it a little more when the set of vacua is still discrete, but the word massive doesn't apply so strictly. So anyway, the infrared limit is the first approximation is to have this set or manifold of vacua and the tunneling phenomena between those vacua, from one vacuum to another. And the famous work of Guyot, Moore, and Witten quite some time ago, where they introduced the concept of the algebra of the infrared, they incorporated those phenomena, this behavior, into an algebraic formalism, something like associative algebras, Lie algebras, and the like. And of course, for an algebraist, it is very exciting to see a physical formalism dressed in this type of algebraic form. So the key structure in such situation is the plane where the central charges take value. So the space of vacuum, let's suppose it's discrete. We have, say, V1 up to Vn, and there we have various sectors, so to say, as physicists say, when we transition from Vi to Vj. And this supersymmetry algebra has its central charge for each sector. And the general physical formalism says that those central charges are additive. They form, if you want, a co-cycle or something like naively, difference of potential energies, Cij plus Cjk equals Cik. So that means that up to a shift, we can assume that the difference of some numbers, Wi minus Wj. And we can think of those Wi as labeling the vacuum. So in principle, it can be the different vacuum, some Cij may be zero, and it's another actually interesting case, but let's consider the simplest situation when sort of it's uniquely labeled. So in this way, the set of vacua is embedded in the complex plane, parameterizing certain charges. So in the infrared analysis, the ith vacuum has what is called the local d-brane category, which in particular situations would be a version of Fukaya-Seidel category. I denote this category by bold-faced phi to indicate some connections with other structures later. So we can think, like naively, that this category sits at this point. So we have the complex plane where there are some points Wi, and each point Wi, there is a category. So typically, it's a triangulated category, such as considered in algebraic geometry, such as Fukaya categories, such as derived categories of coherent sheaves, and so on. And the tunneling phenomena, they give some transport, some tunneling functors, and again, for suggestiveness of the speech, let's call them the transport factors. So Tij from phi I to phi j. This sort of general analysis of the theory even before we specialize any shape of the theory. And the most important example of such theory is the Landau-Ginzburg model. So it is it's a version, or if you wish, you can also consider it's a version of a string theory moving in a manifold. So if you have a point moving in a manifold, it typically moves along a geodesic. If you have on a manifold, you have a potential, then it's standard equations of mechanics. So in 2D sort of stringy point of view, we consider movement not of a point, but of a line object. So altogether, it's a mapping of a surface, two-dimensional space-time, to X. And in order for required supersymmetry to hold, then the manifold X should have a Kähler structure, should have a complex structure and symplectic structure compatible. So this would correspond to a free movement, and the analog of a potential, it should be a holomorphic function on this manifold. So it's a supersymmetric theory that I write here x plus map to x plus some fermionic fields. So it's actually quite some. It's not difficult, but not completely trivial to write the full Lagrangian in this case. So what's important from this Lagrangian, if we eliminate the fermions, that we get what's known as the effective potential, and that is the square root of, absolute square of the differential of the function. So it vanishes when the differential vanishes. So in this case, the vacua would correspond to the critical points of the superpotential. So again, theory is massive if the critical points are Morse critical points, which means that the second sort of the quadratic part is non-degenerate. That again corresponds to the idea that mass corresponds to curvature. So mass is non-trivial, doesn't vanish, that is really sort of convex like this. So, and the central charges, they correspond to the difference between critical values. Cij equals Wi minus Wj. So here on the picture, I have sort of depicted the standard illustration from books on singularity theory, so that you have the level sets of W. So the critical level set has a conical singularity, and the almost critical level are some kind of paraboloids. So in this case, so it's also interesting to consider when the function is not Morse, but singularities are isolated. This is interesting from mathematical point of view. So in this case, you have the space, not the category yet, but the space phi I formed by vanishing cycles, those cycles on those level manifold, which kind of vanish when we contract the manifold. And in the typical situation, that again, this typical illustration, this red thing is this sphere in a Morse situation called delta I is the classical vanishing cycle of Lefschetz. So if it's a Morse singularity, there is only one vanishing cycle. The space of vanishing cycles is one dimension. So this is the most sort of iconic supersymmetric theory. And in fact, as far as I know, there are not so many other sources of theories. And in fact, there is a philosophy that other examples should somehow reduce to this Landau-Ginzburg situation. But this gives us an excuse to focus on this particular case. So let me now recall the formalism of, again, there's a formalism of Lefschetz going back to his 1921 book about analysis, situs, and algebraic geometry. It's from topology of algebraic varieties. We have a function, so here on the picture, we have, on the bottom, I depicted a path in the space where the superpotential takes values. I depicted it as a straight line, but in fact, it can be curved. From each critical point, we can grow what's known as the Lefschetz symbol. And if you have a point in the middle of the path where it is a non-critical value, those Lefschetz symbol would cut there a certain sphere. And from another point, the other Lefschetz symbol would cut another sphere. And there is, you can look at the intersection number of those spheres. It's the number of, again, in the Morse, if we reduce, if, for example, the path is straight, and then we can project the complex plane along that direction, we get a Morse function, and this would be the number of gradient trajectories of this Morse function from one point to the other point. In algebraic geometric language is the intersection number of Lefschetz symbols. Now, this picture has been categorified in the work of Paul Seidel, who used the language of Fukaya categories. So the intersection number is taken in the middle cohomology. So we have a categorification of middle cohomology, which is known as the Fukaya category, a category whose objects are certain Lagrangian cycles of middle dimension. And instead of intersection number, so at the very bottom of that screen, there is morphism in Fukaya category between one such cycle and another such cycle. It's a DG or graded vector space. So what happens on the categorical level, and what are those local categories of D-branes? They are the corresponding Fukaya-Seidel categories. In the Morse case, this category is the simplest category. So let me return to the previous slide. So there is only one vanishing cycle. So the category will be generated by one object, which is this Lagrangian sphere. So it will be the simplest category, the derived category of vector spaces. Is a kind of categorical analog of the base field or of the ring of integers. And the transport factor Tij would be the factor of tensor product with this vector space. So in this way, in this theory, we have an upgrade of the standard, by now standard classical theory of Lefschetz. So now I will explain how the concept of secondary polytopes enters this picture. So this concept was introduced in my old works with Israel Gelfand and Andrei Zlevinsky in the 90s. So the motivation was to understand, the motivation was purely algebraic, to understand discriminants of polynomials in several variables. So we have polynomials with variable coefficients. In order to say this, we need to fix the set of monomials. Then we change the coefficients and look how the zero locus, when the zero locus degenerate. The discriminant is the equation on the coefficient describing when the zero locus becomes singular. So we start with a set of monomials in several variables, which are labeled by integer vectors. And of course, in this case, it is very useful tool to take the convex hull of these integer points corresponding to the monomials. This is called the Newton polytope, or in this language we refer as the primary polytope. And the appearance of the secondary polytope is the polytope whose vertices correspond to triangulations of this polytope. Triangulations with prescribed set of vertices. So it generally has much higher dimension, and each vertex corresponds to triangulations with good generic behavior, which are convex. So in some sense, such a polytope represents some modular space of discrete. It's a kind of discretization of the modular space of Riemannian metrics on the polytope. If you think of triangulation as, suppose given a triangulation, we can form a metric such that every triangle becomes a unit triangle. Then triangulation changes, the metric changes. So this is, anyway, this is this concept which turned out to be quite useful. But in our new approach with Maxime and Jan, we apply this to a different situation when the points are not integers at all. So those are those sets of critical values. So we have some points in the complex plane. If a complex plane is the two-dimensional real plane, so we can form their convex hull is a convex polygon, and we consider all triangulations of this polygon. So maybe I'll write here. So we have some points. We first take their convex hull, but there may be some points inside too, and then we consider triangulations which also involve those points, but do not involve any other points. Something like this. Yeah, so all of them, sort of each triangulation correspond to individual vertex, and somehow the interior points of the polytopes, they interpolate between such triangulations. So, but it's a vertices of the polytope. So our first observation, which we already had in the theory with Gelfand and Zelevinsky, is that the faces of this polytope, if a vertex is a triangulation, then a face is a partial triangulation, is a not yet triangulation, which means it's a decomposition, decomposition into other polytopes, something like this. This is a face, and the vertices inside this face, they correspond to additional triangulation. We can triangulate this, we can triangulate like this. We can triangulate like this, or we can triangulate like this. So that's all, each choice would give me a vertex. So it means that under good conditions, when we can sort of do this independently, the face is the product of the secondary polytope of this, secondary polytope of this, and all of the other polytopes. And this, in modern terminology, is known as factorization. So factorization phenomena in quantum field theory is a very important topic now. So we have a structure which manifestly factorizes. So a face is a product of a face of such polytope is a product of other such polytopes. So this leads to, if you just write chain differential, so we will add d of fp equals product of f, say qi, right? Something like this. But if you look at the level of chain complex, we can write this, interpret this as a differential in the symmetric product. Differential of one generator is a product of other generators. So in this way, if it considers symmetric algebras of chain complex, or just most naive chain complexes of those polytopes, then on this thing, we have a differential as on the commutative or supercommutative algebra. And whenever we have something like this, then the general principle of causal duality says that any such thing is the same as a version of a Lie algebra. Maybe not exactly a Lie algebra in the straight sense, but a homotopy Lie algebra or Lie infinity algebra, algebra with many brackets. But together they are compatible in the familiar sense. And if you try to look at the nature of those brackets, then the brackets have meaning of concatenation, or is opposite to this splitting. So kind of they read off this formula kind of backwards. Concatenation when possible, and when not possible, it is zero. So in this way, we can form an equivalent formulation of the Lie algebra of Gayotta-Moore-Witten, who used the language of webs, and webs in our approach, they correspond simply to the dual picture. So this is a web. So like this, maybe like this. Yeah. So we can think about plane webs and sort of refinement of webs, or we can think about secondary polytopes and triangulations and polyhedral decompositions and their further triangulations. And this factorization property makes the Lie algebra construction very easy. And it makes sense in any dimension. In 2 dimensions, we have an extra feature. So in principle, it can also be pursued in another dimension. But here, what we have is that we add one point at infinity, and this already suggests sort of the Fukaya-Seidel picture with certain things going to infinity in one particular direction. Then maybe I should say this. So near this infinity, we the ordering of for any triangulation like this, we have or any polyhedral decomposition, we have this ordering here. It means that we can define not just a Lie algebra, but an associative algebra. Again, weak associative algebra, because we know in which way they go. It's a refinement. And what we get is that we have a morphism from the Lie algebra corresponding to the finite part to the associative algebra corresponding to the infinite completion. And our theorem is that this is a quasi-isomorphism. So it means in particular that all the deformations come from particular Maurer-Cartan elements in this Lie algebra. And one of the conjectures of Guyot-Moore-Whitson is that some particular Maurer-Cartan element gives the Foucault-Seidel category. And this is kind of puts this in a general framework. So, and now I want to discuss the analogy of this formalism with perverse sheaves. So perverse sheaves are mathematically certain complexes of sheaves on a stratified space. So space which subdivided, for example, into different smooth strata. So X is disjoint union of strata X alpha, which are smooth. But the closure of X alpha may be singular. So here, for example, so this part without the point is a stratum, the point is a stratum, and the complement is a stratum. And one of the reasons to look at them is the Riemann-Hilbert correspondence in its modern form, which says that such perverse sheaves, they are in bijection with holonomic regular D-modules, which are basically systems of linear PDE. Via the functor of solutions, we have a system of PDE and we have the sheaf of solutions. But to do it correctly, we should consider its derived functor, which gives a complex. And the simplest case is we consider when we have, I say C com 0, so this would be, say, C2. Suppose I have C and only one point 0. So then corresponding description is given by two vector spaces, one vector space of vanishing cycles and another vector space of nearby cycles, and two arrows in opposite directions. So the vanishing cycle corresponds to behavior here, and the nearby cycle corresponds to behavior here at the nearby fiber. And we have the condition that those maps U and V satisfy that 1 minus UV and Y minus VU is inverting. If we have several points, then we can do this thing for each point. We can have, maybe again I'll use this picture. If we have several points, so we have one point called epsilon and the point W1, Wn. So for each of them, we can sort of connect them with a non-intersecting disk and get this diagram, which consists of several phi and one psi. It will be one psi here and several phi here. And that it was done precisely by Gelfand, Macpherson, and Sergei Gelfand, Macpherson, and Velonen. So this is such description. And our observation with Jan Söbelman and Lev Sukhanov was this is similar to the infrared formalism. Because if you go from this phi to here and to this phi, it's a kind of tunneling. It's similar to the tunneling. So in a way, our point was that the formalism of Guyot, Moore-Whitson is the same as formalism of Gelfand, Macpherson, and Velonen, or a version of this. This, if you want to do the short slogan, it's like this. So, but this was a diagram of vector spaces, not of categories. In physical application, we have categories. Here, Vadim Shechtman and I made a proposal in 1914, is 2014, on categorification of perverse shapes, which means to replace such data by triangulated categories. And yet the concept of categorification was, probably the term was introduced by Igor Frankl and Louis Crane in 1994, the systematic idea of systematically replacing vector space data by categorical data, linear operators by functors, and looking at higher compatibility conditions. So in general, there are several. General craze is not, the definition is not known, but there have been several particular cases when this has been given an explicit definition. And we are looking at very simple cases. So this situation is categorified to the concept of a spherical functor. The spherical functor, we have an adjoint pair of functors, and we can have the same categorify the difference between the composition and identity as the cone of the adjunction map. If we have several points, we have the same situation. We have a bunch of spherical functors, and we can call this data a perverse schober. We wanted to use the word schober. It's a Germanism, so schober comes from it's a. So it's a version of sort of strength of sheaves. It comes from the German word schieben. As I understand, so something viele Dinge aufeinander geschoben, and the closest Russian word would be Scheibe, I think, which is familiar to Russian speakers. So in this case, we have transport functors. So they are complete analogs of the data classifying perverse shapes. So we can see what we can do with this point of view. So here is our proposal, our sort of dictionary, which we would like to propose. That such theories of this particular kind that we consider, they give rise to perverse schobers on the plane of central charges. So the vacua would correspond to singular points of the schobers when they fail to be local systems. The local D-brane categories are those phi data. And the tunneling effects, they correspond to these transport factors. So, and what we want to say more particularly, that the meaning of the infrared algebra is the Fourier transform, analog of the Fourier transform for such schobers. This matches to the remark which Greg Moore made some time ago, that their algebra is a categorification of the quasi-classical expansion for the standard exponential integral in quantum field theory. Let me now discuss what happens, how such structures appear in the Landau-Ginzburg formalism. So suppose we have a superpotential, which means a holomorphic function. So in this case, maybe I should write, maybe I'll write it later. In this case, we can take fiber-wise integral. We can integrate this function over the fibers with respect to some measure and get a function on the base. We call it LW of A. It's sometimes called Gelfand-Larrey function or something like this. What's the importance of this is that, maybe I'll write this exponential integral e to the, I don't know, I say z w of x dx is the Fourier transform of this LW. So we first project, integrate over the fibers, and then do one-dimensional Fourier transform of the result. But there are several versions of this. First of all, since it's a multi-valued function, this LW, we can we can ask what differential equation satisfies, how it varies, and the corresponding object here is the perverse sheaf. We can write it as a zero perverse homology of the formal direct image. It's a certain perverse sheaf on the base. We call it Lefschetz perverse sheaf. Its data, Gelfand-McPherson-Villonen data, are precisely the classical spaces of vanishing cycles. The vanishing cycles in the sense of theory of perverse sheaves, they would correspond to the vanishing cycles in the sense of Lefschetz, and the psi would correspond to the middle homology. The transport functors would be give those intersection numbers. This first generalization. And then the next generalization, we can categorify even that to a perverse Schober, because at this point, instead of looking at the space of vanishing cycles, we look at the corresponding local version of Fukaya-Seidel category. Again, it requires some definition. If it's a Morse function, that's simply the derived category of vector spaces. And psi would be categorification of the middle homology of the generic fiber is the Fukaya category. So, and we have this categorical formalism. So, in particular, we have the transport functors. Now, let me discuss the concept of Fourier transform of perverse sheaves or of D-modules. So, naively, in the middle of the slide, I have Z goes to del W and del Z goes to minus W. If I have a differential equation or a module over a ring of differential operators, then we can switch W and Z, we can pass from W del W to del Z minus Z. But the initial differential equation, it had a perverse sheaf of solutions. And by Riemann-Hilbert correspondence, if you have a regular D-module, then this, for a perverse sheaf, the regular D-module is unique. So we can do the switch and get a new D-module, which is also holonomic, but not regular in general, because its solutions are exponential integrals. They exhibit exponential behavior. So formally, what happens, we have a new perverse sheaf with only two singularities, so 0 at infinity. And the 0 singularity is regular, at infinity it is irregular. So it can be understood as a local system on C minus 0. So the stock of this would be the direct sum of all the vanishing cycles. But in fact, it carries additional structure, the stock structure, which describes how the rate of growth of the exponential solutions, exponential growth. And the problem of describing this stock structure has been studied for quite some time. And in several works, which I list there, starting from Malgrange, Michizuki, Daniola Kashiwara, and Daniola with other collaborators. So there is one subtlety here. So in this description, in the original Gelfand-McPherson-Villonen description, the transports, they correspond to the curved paths. We go to epsilon, to some point epsilon, and they're here. But in physics, no physicist would do such thing because it's natural to go along a straight line. So only a mathematician will go from this point to this point by going somewhere far away and then back. And all the descriptions that were done before, they were given in this mathematical sense. So with Jan and Lev Sukhanov, we gave a different answer, which resembles and looks like a toy model of the algebra on the infrared. And the difference, the new part, is that we use transport along straight lines. So here is the summary of this. So let me just say that the Stokes data are classified by one matrix known as the Stokes matrix. It acts on the space of all direct sum of spaces of vanishing cycles, which is the stock, the fiber of the new local system. Will be one matrix, will be upper triangular. In order to fix details, we need to fix a direction at the infinity. So we are talking about local system on c minus 0, so basically a local system on the circle of directions at the infinity. So we fix such direction called zeta. So this gives ordering of the points in this direction. The matrix will be upper triangular. And we can, again, play the convex geometry game. We can look at, for points I and j, we can look at all such convex polygonal paths from I to j. And our theorem is that the matrix element Cij is the sum of all such paths. For example, on this picture, there is this path on the right, but there could be intermediate path, for example, from Wi to Wj directly. There will be different path, and there will be some other intermediate things. Whenever convex we can make, so we should add. And for each such path, we have a composition of rectilinear transforms, sort of transports in the physical sense. So now, why rectilinear transports are more important? Well, because in the study of Fourier transform, we are looking at behavior of exponentials, and the exponential function it decays. Any exponential function decays in one hyperplane and grows exponentially in another half plane. Sorry. So those behavior of different half planes, they dictate the appearance of convex geometry. So this is the Stokes matrix of the Fourier transform. So more specifically, we can analyze a perverse schober in different ways. We can fix a point. Here I denoted epsilon. There it's called V, if I'm correct. And we need to do this. So here I said we sort of connect with a small neighborhood which contains only those. The general formalism is that the neighborhood, for example, can go like this. There are different ways of connecting. And this is a well-known structure in singularity theory. We call it spider. There are many spiders for such data. In fact, they form a homogeneous space torsor over the braid group. And we have a change of spiders. We have what's called a mutation in the triangulated category. So for every spider, we have the transport functor. And what we have is an algebra of those functors, or as category theorists say, as a monad. So if we have here the composition of Tjk and Tij maps to Tik in a associative way. Or if you want, yes, it's algebra of factors, if you wish, coming from the adjunction. So here on the next slide, I depicted a situation depicting this mathematical situation when the point V is far away at the infinity. It is what no physicist would do, but this is typical structure in all books on singularity theory. We have a disk, we have a point on the boundary of the disk, which is infinity from normal intuitive point of view. Let's call it an infinite spider. So, but again, one can, from one point of view, it's unnatural. But from the point of view of Fourier transform, it is kind of natural because those correspond to the paths of integration. If you make them into straight paths in going from critical point to infinity, they're precisely the paths over which we do the Fourier integrals. So if we consider algebras over this monad, we get a triangulated category, which we call, so by generalizing the known construction, the Foucault-Seidel of the schober. And similarly, in this case, we can extend this formalism. We construct a Lie algebra, and out of all such triangulations, the corresponding vector spaces would be categorical traces, some kind of Hochschild homology, and will be a similar theorem that will have a quasi-isomorphism from the Lie algebra to the Hochschild complex, the formation complex of the associative algebra. So once again, we can, let me rehash this dictionary. So to a theory, we propose to associate a schober. The theory doesn't have to be Landau-Ginzburg in general, although sort of we don't know much about other theories. So the infrared algebra would correspond to Fourier transform, explicit structure of Fourier transform for schobers, more precisely, explicit structure of the Stokes data for this Fourier transform. So just to finish, we can say that I say that in principle, similar analysis may be possible in other theories, except what we get a new phenomena. We get perverse sheaves and schobers with infinitely many singularities of the kind that appear in theory of resurgence. So, and this is still work in progress with Jan Soberman. So this is the picture, and thank you so much.
Thank you so much for the talk. Any questions or comments?
Thank you. So it's beautiful constructions. Many of them seem to require working over the complex numbers and using some topological background.
Yes.
You have paths. Is there a hope, or maybe you already have done this, to do a more purely algebraic? I mean, the vanishing cycles, they exist in
Yes.
homology. And
no, we were thinking about this, but however, so our approach is intrinsically the caveman approach, which sort of separate into real and imaginary part. And for a pure algebraic geometry, it may seem unnatural, and we are aware of that. So some of this may work, some of this may not. Even you see the Fourier transform makes sense in characteristic P. Yeah. So it would be interesting, but we don't know how to tell the difference between the concept of those curvilinear transports. We don't know how to understand.
I have a naive question here. So it's not necessarily Landau-Ginzburg, but it need to be massive.
What? No. So you see, like massive for us was a sort of symbolic shorthand.
For V being, for vacuum being finite.
Yes. Yeah. Moreover, it doesn't have to be. I don't know the exact physical condition which corresponds to the Landau-Ginzburg potential having isolated singularities, but not necessarily Morse.
I see. But then how about this? I think like Calabi-Yau case, is that applicable to Calabi-Yau case? I think it's not massive.
Calabi-Yau with a potential or without. So I guess we should say that. I should say that we don't know. So here, yeah.
Okay,
yeah. To be honest, I don't want to speculate.
May I simply ask for a few more words about this last comment? So what 4D theories and what's the type of application of resurgence that you have in mind there?
So what you get, let me focus so that I don't say anything completely wrong. So there is in that case, you consider something like we consider sheaves whose fibers are the algebras of functions. So in the condition in cluster structure, we consider cluster transformations which are sort of automorphisms or barational automorphisms of the algebra of functions. So those are, in 4D theories, such automorphisms are themselves interpreted as some kind of Stokes data. So that's one sort of take back from the series of papers of Gayota, Moore, and Niske, the Stokes data. But if we try to make sense of this, then we consider perverse sheaves with respect. We should consider perverse sheaves which are algebras with respect to additive convolution. then the Fourier transform would be an algebra with respect to ordinary multiplication, which would be like a local system of algebras. So, and the stock structure for that would be would give you the cluster transformations. But in order to get to the other plane, so in which sort of to this plane over which the Schober would live, we should consider, so the number of critical points will be infinite. They will form an arithmetic sort of a semi-group or a group. Right? So, and this is the situation which happens in resurgence.
Thank you.
So naive thing. So you start from this supersetting, and then you ended up with perverse sheaf of vanishing cycles. Can you do this for some notion of perverse sheaf of vanishing supercycles?
That so the original geometric source is still a manifold. So supersymmetric theory takes values in an actual Keller manifold. From what I know, I'm not aware of generalization in which the target is a superspace. Yeah, I simply don't know. So it's a general sort of supersymmetry comes from the source, so to say, but not from the target. So I don't know what happens if you try to extend the target. It probably makes sense, but we don't know.
I mean, it's kind of, it gets applicable when you're not looking at just its source and target varieties, but actually a moduli space with potential on it.
Yes.
With superstructure. So.
Well, I imagine that something like this can be applied. Yes, we haven't thought about it. Yeah.
Sorry, I have a simple question. What's the mean singular points?
What's singular point?
Whether it's has the matrix is degenerate,
So the question is, what is the singular point?
What's the mean singular point?
Okay. So we consider an object, so a constructible sheaf, for example. F is a sheaf. So the sheaf is a local system outside of certain points. For example, we have the function square root of z, right? So the determination of square root of z form a local system outside 0, but the behavior changed at 0. So it's a structure of a sheaf. The sheaf is such that singular points are points near which the sheaf is not a local system. Okay, so W single F is F. So near W, not local system.
Okay, thank you.
So let us have that last question, and then we can continue discussion during the break.
So if you consider Landau-Ginzburg with W not Morse, but Morse bot, is it easy to generalize?
We haven't thought of that, but so in principle, the formalism of perverse sheaves makes sense. You probably want to. So the answer is probably yes. We haven't thought about it. In general, if you have any, the concept of vanishing cycles makes sense for any function, with isolated singularity or not. With a direct image, it would have finite set or discrete set of singularities. The only thing is the interpretation of the vanishing cycles in this sense of classification with something on top is more complicated. But in principle, one can trace such things through.
But I assume kind
of
Morse bot.
Yes, we did not. Yes, we haven't looked at that. Yeah.
Let us thank the speaker again.